All right, so here we go. So thanks for joining me again this morning. Let's look at nuclear chemistry, our last chapter for the semester. And it's only about really 15 pages, a very quick one indeed, which will easily get done this week. There will be polling questions for chapter 10. They'll come up on Wednesday morning. And there might be a couple of questions on for homework on chapter 10 as well, but I'm going to have to make those. But as usual, look at a couple of scenarios to start off the chapter. So patient comes into the ward. Everybody can see my screen, by the way, yeah? I'm sharing properly?
Yes.
Okay. Patient comes into the ward with a swollen thyroid gland. Patient's been suffering from nervousness, insomnia, and weight loss. After some blood tests, you determine the patient is suffering from Graves' disease caused by an overactive thyroid gland. You prescribe a series of iodine capsules and the patient makes a full recovery. We'll talk about that and what these iodine capsules do. You have a patient who needs to be referred to the city hospital for a CAT scan. When you research the available dates, you see that the hospital is using two different isotopes for their CAT scans. One is technetium 99 and one is thallium 201. The number just refers to the mass for that particular isotope. Does it matter which isotope the patient is exposed to? We'll talk about that and talk about how it is important, or rather it could be important, to choose one isotope over another, and why one isotope is probably less dangerous than the other. I'm certainly not someone who would disavow any radiation treatment. Sometimes it's the lesser of two evils. But beware and remember there is no absolute guaranteed safe amount of radiation to be exposed to. It's always a risk, even just a little bit of a risk. If it wasn't, these people wouldn't be standing behind LED screens when they tell you it's safe. Okay, so a little bit over 100 years ago, French chemist and adventurer Henri Becquerel discovered by accident that some of the rocks he had collected on his lab desk were emitting a strange form of energy. He realized this because the photographic plates he had placed on his desk next to the rocks started to fog up before he got a chance to use them. An early photography supporter was Becquerel, as well as climbing mountains. And so he realized that something was being emitted from these rocks that caused the plates to fog up. And this was our first record of radiation. Quite incredible, the leaps and bounds we've made in just over 100 years. So radioactive decay is the emission of some kind of matter from the nucleus of unstable isotopes. They emit radiation as they try and become more stable. That's the whole point of chemicals or rocks emitting radiation. They are unstable and they emit radiation to try and become stable. Now they emit different forms of isotopes and often turn into different forms of isotopes because of that radiation. So it doesn't hurt to do a little bit of a refresher on isotopes from what we talked about in the early part of the semester, chapter 2. Remember, isotopes are atoms of the same element with the same number of protons. It's got to be the same number of protons to be the same element, because the number of protons is the atomic number and defines the element. But we have different numbers of neutrons. Number of neutrons means we have a different mass number for these isotopes of the element. Hydrogen is a fine example of that. We've got atoms of hydrogen with a mass of 1 because they have 1 proton but 0 neutrons. And then we have deuterium which has a mass of 2 because we add in a neutron besides that proton. And then we have tritium, which has a mass of 3 because we have 2 neutrons and that 1 proton in the nucleus. And so they're not all equally stable. We'll talk about that in a second. By the way, my headphones are beeping at me. So if I suddenly cut out, send me a message or something, it means my headphones have died again. I think this headset is just on its last days. So we get these different forms of hydrogen, different isotopes of hydrogen. And for the stability of these individual isotopes, it falls into 2 basic rules of thumb. It depends on whether we're looking at an element from the first half of the periodic table, the first 50 elements, or looking at elements in the second half of the periodic table, from elements 50 onwards, roughly. And what we have is for those elements with an atomic number below 50, so all the elements that we see at the top of the table, the stability comes from an equal number of protons and neutrons. And so the mass number is exactly double the atomic number. 6 protons for carbon, of course, but with 6 neutrons to give a mass of 12, that makes a stable isotope of carbon. And we see that the element starts to become unstable as we start to tip the balance and add more neutrons. So carbon 13, which has 6 protons but 7 neutrons, and even carbon 14 with 6 protons but 8 neutrons are unstable forms of carbon. So if there's an excess of neutrons, that normally means that we've got an unstable isotope for that element. Even numbers are what normally work best. Likewise, we can see with oxygen, the stable form of oxygen is with a mass of 16, because we have 8 protons, but also 8 neutrons. But as we add more neutrons, like oxygen 17, with 8 protons but 9 neutrons, we start to become increasingly unstable. So oxygen 17 and carbon 13 are unstable and would emit radiation as they try and become stable. So that's our first rule. Interestingly, as we move to the heavier elements in the periodic table, towards the bottom half of the table, the stability improves as we add neutrons. More neutrons becomes better. So while we have radon 222 with 86 protons, and how many neutrons would that be? That'd be 136 neutrons, I think that is. 136 neutrons or thereabout for the radon. That is stable. More stable than the radon 205, which has 17 less neutrons than the 222. As that mass number drops, it's usually about a drop in the number of neutrons, because the atomic number is staying exactly the same. Similarly, mercury 200, that's a relatively stable form of mercury, 80 protons, but 120 neutrons. But less stable is the mercury 197 with just 117 neutrons rather than the 200. So when we get to these heavier elements, they prefer the isotopes to have more neutrons. That's the ones which are stable. And usually, the more neutrons, the better. So for the top half of the table, we're looking for an equal number of neutrons to protons. So the mass is exactly double. But with these bigger elements, these heavier elements, we want to see more neutrons. And usually, the more the better to get to the more stable version of the isotope. So if we take a look at some examples. Yeah, I get to use my pen again. Okay, let's see. Let's try and get this guy working. Take it over here. Yeah, let's use the blue. So we'll look at the first one, the phosphorus. Now the atomic number is low. It's from the top half of the table. So we want the proton count to match the neutron count. We add another 15 neutrons to those 15 protons. That would give a mass of 30. So a mass of 34 means that we do have too many neutrons. That is not expected to be stable. That is an isotope of phosphorus that would be expected to radioactively emit. The potassium 43 with 19 protons. We would like to see 19 neutrons. That would give a mass of 38, but it's a mass of 43. So that also looks unstable. It would also be expected to emit radiation from the nucleus. Next, when we look at the thorium, because we're now looking at one of the heavier isotopes, one of the heavier elements, we know it's one of the bigger ones because the atomic number is 90. Remember, there's only just a little bit more than 100 undisputed elements. And I think we're up to 117 undisputed or thereabouts. It's a bit fuzzy at that top end with us, in some cases, very little research. We're definitely on the top end. And so we want to see more than 90 neutrons, the more the better. But with that mass of 180, it's still just an equal number of protons and neutrons. That doesn't seem stable, therefore, and that isotope of thorium would be expected to radioactively emit. The americium 95 with a mass of 244. If we had 95 neutrons, that would be a mass number of 190. We've clearly got way more neutrons than protons, about 50 more neutrons than protons, 49 more to be exact. So with the additional neutrons, that does look like a stable isotope. Finally, Einsteinium, atomic number of 99, 99 protons, with a mass number of 198. Mass minus the atomic number gives the number of neutrons. That's an equal number of neutrons again. So that doesn't look like a stable isotope of Einsteinium, and therefore that's something that would be expected to radioactively decay. Any questions about those ones? So when the mass number, when the atomic number is low, we want an equal number of neutrons to protons. But if the atomic number is high, meaning above 50 or thereabouts, we want to see more neutrons than protons for a stable isotope. Everybody still hear me?
Yeah.
Okay. My headset is just driving me crazy. Just beep, beep, beep. I guess just press on. Right, okay. So radiation is emitted from the nucleus, but there are different kinds of radiation that can be emitted from the nucleus. So let's take a look at some of the classics today. First one that you might have heard of is what we call alpha radiation, using the Greek first letter of the alphabet, alpha symbol. And an alpha emission is an ejection of a stream of protons and neutrons from the nucleus. Each time, the atom emits 2 protons and 2 neutrons, effectively. And so we sometimes use a symbol for the element helium to represent that alpha emission, that alpha radiation, because our atom of helium, of course, would have 2 protons and 2 neutrons with a mass of 4. So it's kind of like the element is spitting out helium atoms. Of course, it's not giving off any electrons, So if it was atoms of helium, it'd be helium atoms with a positive 2 charge without the electrons present. So it's not really helium, but you'll often see scientists use the chemical symbol for helium to represent alpha emission. I much rather would see the Greek alpha first letter of the alphabet. So when that emission occurs each time, it's going to cause a change in the atomic number, therefore cause a change in the very identity of the isotope. It's going to change into a different element when alpha radiation occurs. Atomic number drops down by 2 units, and the mass number drops down by 4 units, because we're losing 2 protons and 2 neutrons, which are both, of course, counted towards the mass. So something like uranium 238 undergoes radioactive decay, will effectively lose a helium atom, and so the atomic number drops by 2 down to 90. That makes it an isotope of thorium. Only atoms of thorium have 90 protons. While for the mass number, losing 2 protons and 2 neutrons, we now have a new mass for this isotope of thorium of 234. Next one, radium 210. That alpha emission again, losing 2 protons and 2 neutrons. The atomic number drops down by 2, down to 86, which of course makes it radon. And the mass number drops down by 4 units, 2 protons and 2 neutrons, giving us a mass of 206 for this isotope of radon. Finally, the fermium, mass of 147, alpha emission again, so the atomic number drops down to 98, which makes it californium, and the mass number drops down to 143, as those 2 protons and 2 neutrons are given away. So that stream of radiation, if I kind of make a radiation source here, we send that stream of radiation out into the universe, and if we pass it through a pair of electrical plates, one positive, one negative, before it eventually reaches a detector of some kind, what would happen? Did I get my spelling wrong there? Yikes. Deary dear. There we go. Before it reaches the detector, what would happen to that stream of radiation passing through that electrical field? Any thoughts? Maybe I should just ask someone. Dramatically say, Sid, what's going to happen?
Would it be equal?
Equal?
Like, I'm trying to figure out how to, like, would it neutralize?
Not neutralize, it will definitely pass through, but how would the path of the radiation be affected by this electrical field? Think about what the radiation is made up of. We said it was made up of positively charged protons, but also neutrons, which are of course neutral. So because of those positively charged protons, and it's not just Sid, it's everybody here, what happens to something that's positively charged when it passes through an electrical field like this? Alexei, any thoughts? How would those positively charged protons interact with something that's also positively charged?
Wouldn't it be repelled?
Right, positively charged things repel other positively charged things. Good. And how would those positively charged protons, Maria, be interacting with a negatively charged field?
What was the question again?
So how would those positively charged protons be affected by a negatively charged plate?
Would it stabilize it?
Not about stabilization. How would it be attracted to it or repelled by it?
Oh, attracted to it.
Right. So the protons in this stream would be repelled by the positive plate, but actively attracted to the negative plate. And so that radiation path would bend away from the positive field towards the negative field, and you could actually bend the stream of radiation. So it would hit the bottom half of the detector. So it is possible to a small degree to manipulate radiation as it passes through the air. Okay, just checking people are awake there. Okay, that's often a juicy exam question, by the way. Right, there's a couple of extras. Take a couple of minutes of Zen and give those a try. What would be the new identity of the isotope after these different forms of radioactive decay? Last one, or rather this one here on the top right. If you know its finishes as plutonium, how did it start? Take a minute and try those for yourself. Periodic table would always be useful, of course. Oh, I guess you can look in your phone for a table. Help us if you can see the question. Let me check and see how my baby girl is doing. All right. Let's take a look at these ones. So let's see, let's switch to red. So the polonium 210 loses 2 protons and 2 neutrons. Mass number will now be 206. atomic number will now be 82. Now, is that lead? Let me just check quickly. Yes, it is lead, Pb. For the identity of the isotope. Second one, we're working backwards this time from plutonium. So the mass finished as 244. Before it lost those protons and neutrons, the mass must have been 248. And before the radioactive decay, the atomic number must have been 96, which should make it curium. Yep. Sometimes I mix up curium with californium. Incredible woman, Madame Curie, who curium is named after, wasn't happy discovering one element. She discovered two elements. I don't think there's any other person in the history of science who's done that, discovered two elements. Just incredible woman. What elements were they? I remember one of them is, pretty sure one of them, radium. Yeah, I think it's, yeah, I think one of them is radium. I think the other one is polonium.
One of those elements killed. One of those elements eventually killed her.
Yeah, definitely, and her husband. I think it was polonium was the other one, because she named it after her home country, Poland. Yeah, she used to go around Europe doing demonstrations of radiation. I think it was demonstrating how what effect it would have on plant tissue samples, and apparently never thought, well, I don't know, but didn't seem to think about what it was doing to her own body and tissues. She used to get her husband to carry around a sample in his breast pocket, and I think they found just a big black hole in his left lung when he finally died, and most definitely killed her husband and probably caused her own death as well.
I don't remember if they had kids or not.
That I'm pretty sure they did, because I think her daughter, did I hear a story like a daughter discovered an element as well or something like that? Crazy. I think a daughter became, she definitely was, I think a daughter was published. I need to go back and look at all this history. Incredible stuff. I mean, science, history of science is some incredible stuff. Let's see, thorium, 236, loses 2 protons and 2 neutrons. So mass number goes down to 232. Atomic number goes down to 88, which should be radium. Yes. And if that radioactive decay continues another time, losing another 2 protons and 2 neutrons, the mass number goes down to 228. Atomic number goes down to 86, which I think should now be radon. And then one last time, another 2 protons, another 2 neutrons, mass goes down to 224. And atomic number goes down to 84, which might be polonium. Yes, it is. Okay, any questions about those ones? Are you doing okay? So let's see, oh, look at that time. Duh. Too much time dawdling. Anyway, let's do one more before we break for this morning. And again, we'll have lab this afternoon, our online lab, which will just be going over some practice questions. We'll focus on practice questions for chapter 9. We'll probably do like 45 minutes or something, just to get us active for a bit, and then we'll call it a day. So beta radiation is also a form of radiation which causes a change in the identity of the element, what we sometimes refer to as transmutation. And so with beta radiation, we're getting a stream of electrons being ejected from the nucleus. That doesn't seem possible, I hear you cry, because we don't store electrons in the nucleus. What we think happens is that there are sometimes unstable neutrons in the nucleus that break down to give a proton and an electron. Because the proton stays where it is, it's happy in the nucleus, but that electron is not. And so that electron is ejected from the atom, ejected from the nucleus as a stream of radiation. So although we lose a neutron, and that would drop the mass by 1, we do gain a proton, so that keeps the mass constant. There's no change in mass with beta radiation. But we have caused a change in the atomic number because we've got one more proton than we started with. So for beta radiation, the upshot of this is the electrons are ejected, is that the atomic number increases by 1. So we're again seeing a change in the identity of the element. A couple of quick examples. Phosphorus 32, losing a neutron but gaining a proton. So the mass stays the same at 32, but it's now 16 protons, which makes it an atom of sulfur, and the electron is ejected. Carbon 14, neutron changing into a proton. So the atomic number increases to 7, which makes it nitrogen, and the electrons are ejected. Potassium 40, a neutron changing into a proton. So we have still a mass of 40, but now an atomic number of 20. And so we've got an isotope of calcium. And we can see with these particular examples of beta radiation, how we're taking unstable isotopes with an uneven number of protons and neutrons and turning it into a stable isotope each time because they now have an equal number of protons and neutrons. So as my headset, just beep, 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 going crazy at me. So let's finish this off before I start to lose sound. So the bismuth 211, that would stay as 211. The atomic number would go up to 84, which as we said before is polonium. Another stream of electrons ejected, still a mass of 211, but an atomic number now of 85, which should be astatine. Yep. And then finally, a stream of electrons ejected one last time, still a mass number of 211, but an atomic number now of 86, which makes it radon. Okay, any questions about those ones? So again, we'll put up a link in sometime in the next hour for lab this afternoon. Mandatory attendance. I will be taking attendance, and we'll get everybody to put their video camera on, I think, because I will not be recording it. You want to do some revision, you got to be there. Okay. Right. I shall see everybody in just a little bit more than 2 hours. Have a good lunch, and I'll see everybody soon.